when was the last lecture? So not Friday, last Thursday. So a long time ago for you now, since you're used to have everyday lecture on each topic. So I hope you remember where we stopped. So we stopped at the definition of a Lie algebra. So what is a Lie algebra? So a Lie algebra is a vector space with a binary operation. So I'm just going to recall. So vector space. So it's an algebra, or I don't need to recall it's a vector space. It's an algebra. But the binary operation is going to satisfy some specific property. And so this binary operation is what we call the Lie bracket. Okay? And it's going to satisfy some specific property, which are, so do you remember? It has to be antisymmetric. Okay? So this for any element of x, y element of your algebra. And it's also satisfying what we call the Jacobi identity, okay, which is this here relation so you have to do some linear permutation here, and then you get which is so the Jacobi identity. Okay, so now what are and so what was the first definition I gave you of a Lie algebra is that it's the tangent space at the identity element of the group. So if you start from a group, okay, you look at the tangent space at the identity element, then this is what you call your Lie algebra. Okay, so this is the way we are going to build our Lie algebra. So let's start, for example, with, so I gave you a list, a catalog of group, if you remember. So let's start with one of these groups. So for example, SON. So do you remember what is this group? So this group is preserving distances and angle, okay? So this means that it's preserving the scalar product is invariant. So we can characterize this group by set of matrices. Let's call them like this, depending on one parameter. And of course, t equals 0 will be the identity element here, such as you have that. So these are n by n matrices with real parameter here. And you want to have that the action on some vector is still, so the scalar product is in change, okay, is not modified. So this is the definition of this group. So now how can you characterize the element of the Lie algebra? That I'm going to use this notation here. So knowing that the Lie algebra is the tangent space at the identity element of your group, how do you get if you know the definition of your group here? What do you want to do? Yeah, so we're going to differentiate, for example, this relation with respect to this parameter t, okay, to go to the tangent space, and then, but we want to go to the identity, so then we perform t equals 0, okay? So here, we're going to go from here to here, we differentiate. And then you're going to put t is equal to 0. Okay, so I let you try to start from this relation and see what you get if you differentiate this relation. And let me know. So I let you 1 minute maybe to try to let me, if you can characterize the of course, here, as I said, we consider that is the identity. Okay. Okay, so what are the elements? How do you characterize the element of this Lie algebra, SON? Yanel, you have an idea? If you differentiate this, what are we going to get? So we're going to get something like, and then I put to 0 since gamma 0 is 0, so we get this relation. Okay, so this is an n by n matrix. Let's call it, for example, T. So what does it mean in terms of component here? This means that I will get something like okay, so what do you get? What are the elements of SON? How do you characterize them?
Symmetric.
Yeah, okay, so SON is a set of skew symmetric n times n matrices. Okay, so this is really the receipt you can apply to any group we have seen. So now, where the other group So you can do the same. I'm just going to give you the result for the next group. So yeah, of course, if you look just at the linear group, okay, meaning the set of invertible matrices, then you will just find that this is a set of real, the algebra is just a set of real matrices. But then if G now is your unitary group, UN, in fact, you will get the same result here. It's skew symmetric n by n matrices. Okay, so if you get UN, then you get that is a set of and now if you look at SUN, in fact you add here you will get again skew symmetric. Here you will get the same, except that you add a condition that you want the trace is equal to 0, okay, null trace. And then SON and ON are the same, also are characterized by the same kind of matrices for their Lie algebra. Okay, so these were some examples. Any question? Yeah.
If it's skew symmetric, are all the diagonal bits not already 0?
Yeah.
So the trace is already 0?
Sorry. Here, no, but here it's not real. Okay. So yeah, maybe it's skew. Yeah, it's not real. This one. Okay. Yeah, and in fact, it's more Hermitian here. It's not symmetric. Because we are in the, it's complex matrices for UN is a complex. you were considering complex matrices. Yeah, thanks. Okay, so now what is the next point? Let's have a look at what we call generators and constant structure. Okay, so what are the generators of a Lie algebra? Okay, so if you remember on Thursday, we started also, we looked at another example. We looked at the rotation matrices, so matrices of SO3, okay. And I asked you to write the 3 matrices given that the 3 rotation, on the x-axis, y-axis, and z-axis. And then we did exactly what we did here, okay, starting from these three matrices, meaning that we differentiate with respect to theta, then we computed everything for theta equals 0, meaning that we ended up in the Lie algebra, associated Lie algebra. And here we obtain 3 elements, 3 matrices that I call J. And in fact, these J are really what we call the generator of SO3. And here you can see that the dimension of your Lie algebra, seen as a vector space, is dimension 3. Okay, so you need 3 generators. So what do we need? What are the generators? In fact, they are just a basis, okay, of your Lie algebra. So for any algebra now, let's consider a finite dimensional Lie algebra. You can always define a basis characterized by a set of elements where A is going to, in your Lie algebra, let's call it G, with A is going to take the value from 1 to D, where D is going to be the dimension of your Lie algebra here. And this TA is what we're going to call the generators. Okay. And you have seen that here, a very important object in the concept of Lie algebra is this Lie bracket. So of course, we can now look at the Lie bracket between 2 generators. And this element now is still an element of your Lie algebra. Okay, so this means that you can express that, you can decompose that on your basis, of course, and so this means that you can write this result as a linear combination of your generators, and this coefficient here as what we call the structure constant of your Lie algebra. And in fact, this coefficient, so when you know generator and the structure constant of your algebra, then you know everything about your Lie algebra. Okay? So these are really the fundamental objects here that you need to determine. So for example, if we go back to this example, so you remember that you obtain 3 matrices. So here, how do you get the constant, the structure constant for SO3? You just compute the generator between Gx and Gy, Gx and Gz, etc. And you get that, so for this example, we'll get that. So if I call I, J the different element, then you get that this is epsilon ij. Okay, where here it's a totally antisymmetric tensor. Okay? So this is the first example, and these are the structure constant of SO3. So since these constants are so important, let's see if we can determine together some of their property. So if here I'm calling, so this first starting from the fact that you have that the Lie bracket is antisymmetric. What can you say about what does this impose on the structure constant? Yeah, for which indices?
Ij. The first two.
Yeah, okay. So this means that you also have Okay, so you have the antisymmetry with the first two indices. And then, of course, if we now look at the Jacobi identity, we get a new identity for this structure constant, okay, which is also usually called the Jacobi identity. Okay, it's exactly the same to have this relation of the structure constant and to have this. Then this will imply the Jacobi identity on the Lie bracket. So I'm going to, if I don't want to get confused with all the indices, so if you do it yourself, then you get this relation, which is the Jacobi identity for this DCE plus FCAD. So I'll let you check that I haven't done any mistake with all these indices here. So you just really have to rewrite your Jacobi identity using the replacing each Lie bracket with this expansion on the basis using the structure constant. And of course, because of this property, this means that here you get that FAC is equal to 0, okay? Obviously. Okay, so any question here? So what do we have now? So at the beginning of the lecture, we started with groups. Then we said that we can go to the tangent space as an identity element to go to the Lie group. So from the given Lie groups that you know, we can determine what are the associated Lie algebras. Okay. And now, how do we characterize this Lie algebra? Usually, we like to have a basis, and this structure constant are then really important objects that characterize completely our Lie algebra. Okay. But so now, if I'm just giving you a Lie algebra, can you give me a group, a Lie group? And the answer is yes. We already have seen that quickly in this example. If you remember, then you use the exponential map for matrices, okay? And you end it up with going back to this group element, okay? So from a given Lie group, you can always define the associated Lie algebra, okay? Any Lie group as a Lie algebra. Then for any Lie algebra, you can always define a Lie group. Then this map is not usually unique. We are going to see that in the tutorial this afternoon, for example, that SU2, and I already gave this example, but SU2 and SO3 have the same Lie algebra, okay? So usually with the exponential map that I'm going to introduce now, what you're going to get, the group you're going to get is the connected and simply connected Lie group, okay? So let's first introduce what is this exponential map, and then I can come back on this definition of connected, simply connected. If this is so the map, the exponential map is going to be a map starting from the Lie algebra, and then it's going to give you a group element, okay? And it's a smooth map satisfying these three properties. So what do you want to satisfy? You want, of course, that the exponential of here 0, so 0 here has to be seen as a, if we talk about matrix group, is a matrix, because here this gives you the identity of the group, the identity element, okay? Then you have that the exponential is, of course, linear, so the product is going to be exponential of and this for any ST are real number, and X is an element of your Lie algebra. And what I'm missing a third one. Yeah, of course, then it's, so this is the first. The second is now, if you differentiate your element and you evaluate at t equals 0, then what do you get? No, so t is just a real parameter. X is a Lie algebra element. Yeah, so you get X. Okay, so here X doesn't, of course, usually we are going to write things using the generators, but it's just an element of here, the Lie algebra. Okay? And so in the case of a finite dimensional Lie group, you can always write an element G, at least when it's close, is in a suitable neighborhood of the identity element in terms of generator, like this way. Okay, so this can always be done for a finite dimensional in terms of generator. But sometimes it's only in the neighborhood of the identity. And in the case of compact connected Lie group, then any Lie group can be written this way. Then for non-compact cases, sometimes you do not have access to the complete group. Okay, so you see that there are some subtleties. Okay, so of course, going from, so if we go back to what we started. Okay, so starting from a group, you can always go define the associated Lie algebra. Okay, you just need to define. So this is a manifold. You just need to define the tangent space at the identity element. Okay, so this can always be done. Then, so here it's differentiation. Usually how you do that explicitly, you differentiate and then you evaluate close to the identity, or close at 0. Okay, and then for here we have seen that we have this exponential map. Then this way is a bit more subtle in the way that first, this group is not always unique. Okay, and then in some cases, especially when you have a non-compact group, then you don't always have access to all elements. Okay, so you have to remember that, of course, we can always take the exponential. You will always get some group element, but then the question is, can you span the full group? This is not always the case. It's a bit more complicated. And so for any here Lie algebra, there is a unique Lie group which is connected and simply connected. Okay, so for example, if we start from here, we have said that SU2, and you're going to see that during the tutorial, is going to be the same as SO3. Okay, so it's the same algebra. So you call it the way you want. Then with the exponential map, in fact, what you get is going to be SU2, which is connected and simply connected. So you remember that SU2 is more or less the 3 sphere, okay? And the 3 sphere, so what does it mean that it's connected? Everything, is that clear for everyone? This means that for any 2 points can be related by a path, okay? A continuous path. Then simply connected, what does it mean? This means that if you have, you can always, this path between any 2 points can be always deformed continuously in, so if it's a closed loop, it can always be deformed continuously to get a point, okay? So for example, what is not simply connected, I think I already gave this example, it's the torus. Why? If I'm looking now at this path here and this path here, okay, they are both related to the same point, but you cannot deform this path continuously into this one around here. Okay, so this is not simply connected. Of course, on a sphere, you can always deform any closed path in a point continuously. Okay, so this is simply connected. So SU2 is connected and simply connected, but SO3 is not, and you're going to see in the tutorial that indeed, if I give you an element in SU2, then the associate you have the associated rotation, okay, you still have a isomorphism between that, but it's just surjective, then you have this relation, okay? And so we're going to say that SU2 is a double cover of SO3, okay? So, but this is you're going to study this a bit more in detail this afternoon. Okay, so this was just to say that, of course, the exponential map, you can always define groups element, but then you cannot always have access to the complete group, okay? So you have to be a bit more careful with that. And another important application of the exponential map is that it relates representation, okay? Of a Lie group with the one of its Lie algebras. And in the case of a compact, again, Lie algebra, so if here we have a compact Lie algebra, its finite dimensional representation are going to give the representation of what we call the covering group, which is the covering group is just the group which is connected and simply connected. Okay, so in the case of this Lie algebra, if you look at the representation, you start from the representation of the Lie algebra, you apply the exponential map, you're going to get the representation of SU2. Okay. Okay, so it's also, yeah, so you have also a link. So what is also important application is for the representation, okay? Lie algebra Lie group. Okay, and so the detail I just mentioned are on the intellectual note. I'm not going to write everything. So now, so we already mentioned a bit what does it mean to have a representation for a group, not a Lie group, so I'm going to come back on that later. But first, let's look at the representation of a Lie algebra, okay? So any question here? Yeah?
I just didn't catch, so they're actually not isomorphic, SU2 and SO3?
No, you don't have a... So it's not one-to-one, it's two-to-one, okay? Yeah. Any... So let's move to the next part here. So the first thing I remind you this morning was this definition of a Lie algebra. And you see that this definition is quite abstract. It's just an algebra. So what is an algebra? It's a vector space endowed with here this specific binary operation, which is the Lie bracket. Okay? And of course, in math, you could work only with that at the very abstract level and be happy with that. But you guys are more or less going to do physics at some point, I guess. So in physics, to make at least contact with physical system, it's nice to have a representation of this object. So what does it mean? In fact, what do you want to know? It's to know how Lie algebra are going to act on a given vector space. Okay? You want the action on some space, which could be the space of your physical state. Okay? So instead of keeping this just abstract definition, let's now look at the action of a Lie algebra element on a given vector space and try to see what this means. And this is what we call the representation. And let's see if a representation always exists for any Lie algebra or if it's not the case, etc. Okay? So here, let's go to the representation. Notion of representation, and in particular, we're going to talk mostly about representation matrices. Okay, so here, what we want to make precise is the action of a Lie algebra of any Lie algebra element on a given vector space. So what does it mean, this? So again, a representation, and so for this we need to introduce the notion of representation, and so representation of a Lie algebra so it's going to be a map from the Lie algebra itself to the space of linear mapping from V to itself. So if I call my vector space V here, so this means that I'm considering, so this is the space of linear mapping And what do we want about this map? We want that this map is a homomorphism of Lie algebra, meaning that for any two elements here, x and y, which are elements of the Lie algebra, if we look at the commutator, we want that here, the commutator of, so if you start with x and y, here you will end up with, and we want that the commutator here exists of these two elements, and we want to have something like this. So if I'm using this star notation to, here it's the composition of map. Okay, so we want to have this minus and this has to be equal to the representation of the commutator of these two, of the Lie bracket of these two Lie algebra element. And so if we have this means that here we have homomorphism of Lie algebra. Okay, so this is a representation. So a representation R is a map going from the Lie algebra to the space of linear mapping from, so if we want to represent on the space V, okay, vector space V, such as we have that the composition, the commutator of the map is the map of the Lie bracket, okay?
But we can equip the space of linear mappings from V to V with for any vector space, we can always equip it with a Lie bracket to make it a Lie algebra.
No, so Lie algebra is always no. So usually it's more the other way around. So Lie algebra is a vector space, okay, but not all vector space are Lie algebra, okay.
What I'm
so you cannot always.
My question is if the second space, so if GL is also probably going to be a vector space.
Yeah, it's a vector.
Is it going to be a Lie algebra always?
But if then usually we're going to use matrix representation, and so in this case, yeah. Okay. So in the case, and this is what I'm going to just add now. So usually we're going to go in the matrix representation. So we're here in this composition of maps. In fact, it's just the product of matrices, and then indeed this is it's a Lie algebra of the linear.
Yeah, but in order to be a representation, by definition, it has to be a map to another Lie algebra.
Yeah. Okay, so is there always a representation of a Lie algebra? Of course, there is always one, which could be what we call the trivial representation, which is a map that each element of the Lie algebra is going to be mapped to 0. okay, to the zero map, not to zero, but to the zero map. And then this is, of course, a representation that you can always do, but this is what we call the triviant representation, and it's not usually very interesting. So do we have another one? And as you just mentioned it, of course, a Lie algebra is a vector space, okay? So, of course, we can always represent a Lie algebra on itself, okay? And this is what we call the adjoint representation. So this is the next part. And this adjoint representation exists for any Lie groups, or any Lie algebra. And so let's try to clarify what does it mean to, so here this means that we want to represent G on itself. Okay, so what would this mean? So let's first look, before doing that, let's first look at the generator in detail. Okay, so usually, as I said, you have a set of generator. And let's now consider that we can, it's always what we're going to do, we can have a matrix representation. Okay, so this generator are matrices, so I can look now at the component of the matrix entries. Okay? So what A can go from, I said, 1 to n, and let's say that ij can take the value from 1 to another value m. So what is here n and m? N here is going to be the number of real parameters that of your group you started with. Okay. If you remember, for SO3, we started with these 3 rotation, so 3 angles, the angle around the rotation around the x-axis, y-axis, and z-axis. Okay, so we had these 3 parameters, and then we ended up with 3 generators. So it's also the number of generators that you need of your basis, and it's so of course it's the dimension of the algebra itself. Okay, so here n is the number of generators, and it's the dimension algebra itself. And now, what is M? M is the dimension of the representation. Okay, so here, when you go from here to here, you don't necessarily have the same dimension. So here, M is the dimension of the representation. And you see that they don't have to be the same. So what does it mean here? So this means that these TA, of course, are going to span an n-dimensional vector space. But then here, you represent them as m times m matrices, which are going to act on an m-dimensional space, of course. Okay, so these two numbers doesn't have to be related. So now what is the adjoint representation? In the case of the adjoint representation, of course, what do we have? What is the relation between n and m here? Yeah, n is equal to m. And so here, this means that now this TA, we are going to choose the representation where the TA are going to act on the vector space formed by the generator themselves. Okay, so this is the adjoint representation. So here, so formed by the generator. And so now, since instead of in the to make clarify that now I'm in the adjoint representation, I'm going to call this generator with a big T, okay? And how are we going to define this representation now? Here you still have some Lie brackets. Okay, so in fact, you can represent, we can define the adjoint representation as follows. So I'm going to, let's look at which notation I use here. Yeah, BC. Where here, these are the structure. Constant. So the matrix element of your generator are given by, so we add this just because here I want to have, yeah, Hermitian operators, but you can, yeah, in some, it's just a convention, okay? Okay, so now we need that to prove that this indeed is a representation. And for this, let's start with, maybe I erase it, with the Jacobi identity. And I'm going to try to ask you to find, so if I rewrite the Jacobi identity, so starting from that, from the Jacobi identity, can we show that indeed this is a representation? And first, so the first step is, can you compute here the commutator between any TA and TB? Okay, so I let you 1 minute to start doing the calculation. I need some space. I'm going to make some space here. But you can start and let me, like this, you will be able to let me know the different steps to perform. Okay, so what do you need to use here? So of course here I could multiply this equation here by minus each f by minus I, okay? And it's just that at the end, you get the same equation with the minus, but since it's 0, you don't really care here. Okay, so we can really say that this equation is going to be written in terms of matrix element of this T. Okay? So here, what do you get? You get T A with the component CD, and here it's T A D E. Sorry?
PBCD.
Ah, yeah. Yeah, that's better. Thanks. I was like, oh, what is this new? So what do you get here? How can you simplify this first? Or maybe let's write first the equation. So T A B D T C D E plus T C A D T B D E is equal to 0. Okay? Is that clear for everyone? So what do you get here? Here, what's this element? Can you simplify? So here you have to say that, so this is a matrix. These are the elements of the matrix. And of course, here, is that clear to everyone? When you have two indices the same, what does it mean? Yeah. Okay. So here, what is that?
TB and then subscript CE.
TB.
TBTA.
Yeah. Right. Okay. Yeah. Okay. So this means that here, it's the product of two matrices you are looking at. Okay. So here it's using the Einstein notation. Okay. And so here you will get something in. Do we need this one or? See. Yeah, but maybe I should have done some rearrangement before that, because here I'm not going to get the commutator. So I want to get the commutator, so maybe I should have rearranged. So I started with AB, E. So maybe here I could have changed. So if I want some, here I have AB, so this is fine. Here I cannot get AB, but I could get AB from this one. So here I could rewrite this using the fact that it's antisymmetric. Okay. So here I could get minus ACD. Sorry for the confusion. So here now, this is also, so there is a minus. And I got TACD. And so now it's TAB. AB, but the coefficient now it's CE. And it's the same as here. Okay, and so this one, I'm not sure to. So what do I get here? So let's keep TA and these are the coefficient CE and and this term, so here it's like if I have multiplied by I. So if I don't multiply, see if I let, for the moment, the matrix, this constant structure, A, B, D. Okay, so for the moment what I did is that this, I replaced that by, in terms of the matrix element, for these terms too, okay? Just using the antisymmetry here of the structure constant. And now I'm left with this one, so with a minus, because here to go from here to here, I need to multiply everything by minus. So if I have that, because what I want at the end is A, B. So I want the same group element here. So I would like that. I want to keep the CE. So A, B.
Why is the last term negative now?
Plus.
Yeah.
It's a double I.
Here.
Yeah.
So here I multiplied, to go from here to here, I multiply by minus I, okay? Each of them. Except, so here if I multiply also these two, then I get minus I squared. So this is correct, no?
Yeah.
Can you say that again?
So here, to go from this line to this line, I multiplied each of these f by the minus I here. Okay, so it is like if I was multiplying the complete line by minus I squared, which is minus 1. Okay? And then, of course, here the minus 1 are you don't see them because it's inside this T definition. Okay?
Then the minus gives a plus, and the i's give another minus. So TPA.
And so what is that? So this can also be written minus F A B D. And this is also minus I T.
Because the minus are go into the
So let's do step by step. Okay, so now I'm going to use again the antisymmetry here. So this is a plus now, DCE. And how can I write? Now I'm going to say that this is indeed minus I TD with component CE. Okay? So now, what do I have? Everyone is, sorry if it's a bit like... So what do I get? The first line is TB, TA minus TA, TB. So these are, it's just a matrix. And I'm looking at the coefficient and at the entry CE. And I have this plus I F A C D T D C E equals 0. Okay, so you see that this matrix element is equal to this matrix element. So I can now, since this is valid for any matrix element, I can forget about. And what do I get? So this is the commutator. I can now write this in terms of just matrices. The commutator of B with A is equal to.
And the C is not
Yeah, the C should be a B. So is that the case? Yeah, good.
A, B, D.
And this is minus A F I B D TD. And if now we rewrite that this is also minus TA TB, we get the expecting result, meaning that sorry, what the Okay. So indeed, these matrices that are made of structure constant furnish a representation of the Lie algebra. And now let's define a notion of inner product. Okay, so everyone agree with this calculation now? At the end, I think the signs are finally correct. So this is a way to define. So here I introduce you how to define the matrix element, and you see that indeed they define a representation of your Lie algebra. So now let's try to introduce the inner product here and see what we can say from that. So an inner product on the vector space spanned by the generator and we're going to say that TA scalar TB is defined as the trace of the product. So what does it mean here? The trace is just the trace of a matrix. Okay, so in terms of matrix element, what do you get? Here again, here I'm using the Einstein notation. So this means that when two indices are repeat, this means that there is a summation involved. Okay. So here so this is just the product. What is the product of TA with TB again? So this is exactly that. So what does it mean? This means that I'm looking at this matrix and I'm taking the trace. So this means that I'm summing all diagonal elements. Okay? So this is exactly what I'm doing here. CC means that I'm taking all diagonal elements and I'm summing them. Then since this is a product of two matrices, I can also write using the product rules. And so here I'm just writing for a given element CC, I'm just writing what is the expression in terms of the matrix element, okay, of TA and TB. So everything is clear. Are you all familiar with this Einstein notation? Can I go very quickly on that? Or? So you said yes? Okay. There is no here, because I need to know that now. Because then, okay, it's so. So that's why I'm re-explaining a bit now. I know that maybe for some of you it's a bit slow, but it's also the point of these weeks before September. Because in September, then you're going to start GR with indices everywhere, summing everywhere, and it's going to be very quick. So I just want to check that everyone is okay with that. Okay? Great. And in fact, you can show that for any compact Lie algebra, you can choose a basis such as, so you can choose. So if you have a compact, which you're going to be. You can choose a trace such as a scalar product where you have with lambda greater than 0. So in this case, now using that, you could prove that in the case of a compact, so I'm going to do this proof just to make some, so I know that maybe it's a bit long, but it's just to get you, that you get used to this structure constant and to manipulate this object with many indices already, okay? So now, using that, let's prove that, or maybe you can do it yourself. let's prove that the FABC are completely symmetric in all the indices. Okay, so how do you do that? And in fact, what I'm going to prove here is that they are antisymmetric in the last two indices. So for this, I'm going to consider the trace of these matrices, TA, TB, so the commutator of these two with TC. And so this is equal to, now I can replace TC by its expression in terms of the structure constant. So this is just, oh no, I'm not going to replace this one, sorry. I'm going to use this nice result we have here. Okay, so this is equal to I FAB D TD and then times still this TC. Okay, what else can I do? I can rewrite this just expanding the commutator here. So I get TA TB times TC minus TB TA times TC. And here I just have, this is just a number, okay? So you can go out of the trace, which is here linear, and so I get the trace of TD TC, but I'm using the fact that I'm working with a compact Lie algebra, so I can choose my inner product this way. So here I get a delta lambda delta DC, okay? So here I get I F A B D lambda delta DC. Here, what can I get? So this is linear, so this means this is the trace of this matrix minus the trace of this matrix. Then you know that inside the trace, you can always permute your circularly your matrices here. Okay, so you know that you have the trace of AB is the trace of BA. Okay, so here I'm using that. So here I'm going to do this operation on this first term, and here I'm going to do this one here. So what do I get here? I get, this is also the trace, and then I'll reform the trace. So it's TB, TC, TA, minus TC, TB, TA. Okay, so here I can simplify this delta, and I get just I lambda F A B C. Okay. So here, what do you see now? You see that we have the commutator of TB with TC appearing in this term. So if I go from here to here, this is also the trace of TB with TC of the commutator times TA. And of course, this is still equal to I. Let's keep this side like this. But from this side, what do you get? Again, TB, TC, it's equal to I, F, B, C, D, TD, TA. Here, nothing has changed. Using, again, the fact that this is a number, so the trace of TD, TA is just a delta, I get I, F, B, C, A is equal to I with a lambda. Lambda, F, A, B, C.
Is that the same lambda as before?
Sorry?
Is it the same lambda on both sides?
Yeah. Okay, so it's just a normalization factor that, in fact, we are going to see that we can remove. Okay? So the only dependence in A, B here is in the delta. Okay? Then the lambda is completely independent. Good question. Okay, so here this means that indeed this can disappear. And since the constant structure is antisymmetric, so this we know in the first two indices here, what we get is that, so this term BCA is also minus CBA. And this other term here, so which is also minus FBAC, coming from here using the antisymmetry of the first two indices. But this is also equal to FA. So what I wanted to show here. So yeah, and this is, okay, so I can stop here, sorry. So this means that here FBCA is minus FBAC. Okay, this is what I wanted to show. So this means that it's antisymmetric in the last two indices, and going from here, then you can show that it's completely antisymmetric with all indices.
I have a question.
Yeah.
Why wouldn't you just, if you can rearrange the order of the matrices in the trace up on the top board, why wouldn't you just make them?
No, you cannot rearrange the way you want. Okay, you can just do a circular permutation. Okay, so you cannot do TB-TC. The trace of TB-TC is not TB directly. Okay, you cannot. Roger.
Oh, so that.
So here, what I'm doing is just considering this is one matrix. Okay, so you have AB is always trace of BA. Okay, and so here it's exactly what I'm using. Okay, where here I'm using this grouping of, so this is A, B, so it's the same as BA, or AB, the same as BA. Okay? But you cannot swap.
When you say that's true for a compact Lie algebra, you mean it's true for a Lie algebra of a compact Lie group, right?
Yeah. Okay. Of course, then this lambda here, or the structure constant, could be always multiplied by a given by a constant, and you will still define the same group of the same Lie algebra. Okay, it just means that if you start from A and you go, for example, F, and you go from F, where this is just a coefficient times F, okay, what do you mean? You still define the same groups, the same Lie algebra structure. It's just that this means that here you're also redefining your T, okay, your generators. And in particular, this means that here, instead of a lambda, you could choose a normalization where lambda is equal to 1. Okay, so this is just to mention that, of course, the structure constant is defined up to normalization. Okay, so now in this basis, so we have a basis, we have a scalar product. How do the operator act on the vector basis that we have? Okay, so if here we have a state, we see that here we define our vector basis, or our now matrices. Operators are going to act on this vector basis. Okay, so let's finish with that. Uh-oh. So now in these bases, what is the action of the operator TA on, well, I can use, yeah, I don't know if I'm using the same notation. Or here I kept the same. So what is this action? So here, to find this, we can insert the identity element given by, where here again I'm using Einstein notation, so TC meaning again summation on C has to be understood. So now TA can be written as sorry, I'm not going to introduce the identity here. I want to find what I need is element of matrices. So TC, sorry. But I should have, yeah, in fact, sorry, I'm going to define. It's going to be confusing with the same, maybe later. So here, I don't know if it's going to clarify. I'm going just to denote my vector basis with a small t. Otherwise, it's like too many. And are defined using this scalar product, okay? So here, and of course here, so this gives me the matrix element of, in this basis, of my matrix A. And again, we have seen that this is minus the definition of the adjoint representation is this is given by the structure constant, okay? So what do we get here? This gets that TB, TA on a given vector in my basis is given by TC, where again I'm using Einstein notation. And in fact, this could be also rewritten as, so sorry, here I guess it's CB, so here it's also CB. Okay, so CB, which is also plus IF, since we have seen that it's also antisymmetric in the last two indices, in the case we have considered. And so what does it mean? This is also, this is just a factor. It can go inside my vector. And this is exactly how we define the commutator between. And so this is my action. And indeed, in most of the textbooks on Lie algebra, when you are going to see the definition of the adjoint representation, you don't often see that you can write the matrix element of your generator using the structure constant, but usually it's defined this way, okay? So you just say that the adjoint representation, so we can denote it like this. So we start from any Lie algebra to itself is given by the action is defined with the map defined as on y is exactly given by the Lie bracket between x and y. And as an exercise, so this is the definition you will usually find in most of the textbooks, okay? But of course, as we have seen it, you can also define the matrix element of your generators are the constant structure, and this is the same thing. And just to finish, if you want to manipulate a bit this definition, you can try to show, so I let you do that, then the solution is in the lecture notes, shows that if you look at the adjoint, the action of the map, and then you take the commutator here, acting on an element Z of your Lie algebra, this can be also written as and of course this tells you that this verifies the property of homomorphism of your adjoint representation. Okay, so I'm going to stop here this afternoon for the tutorial. In fact, you're going to work on that to try to define all the irreducible representation of this, and we're going to come back on that tomorrow.